to welcome you all to another lecture on the design of seismic resistant RCC building. In our previous lecture, we discussed on the design of staircase. We looked at some codal provisions and we looked also at the detailing of staircase. Today we will look at the design of a staircase in Excel sheet, and I have prepared this Excel sheet only for the purpose of making this video lecture, and this is not an Excel sheet with all the shortcuts or formulas linked wherever necessary. This is just an Excel sheet that I have prepared for the purpose of this video only. And if you want a design Excel sheet in which you just have to input some data and the Excel sheet calculates all the other information, or the Excel sheet calculates the design results by itself, then you can search on the internet also for that Excel sheet, or if you comment with your email address under our video, then I will be able to provide that Excel sheet also. So before starting this lecture, I want to request you all, if you like our videos on our YouTube channel, or if there are any suggestions or any feedbacks for further improvement, then you can comment on our videos, and then you can also like, share and subscribe our channel. So let's start with today's lecture, design of dog-legged staircase. We discussed in our previous lecture that the most common staircase type in residential buildings is perhaps the dog-legged staircase. We discussed about the various types of staircase in our previous lecture, and we will design a particular type of staircase in this lecture, that is our dog-legged staircase, which is supported longitudinally. So if you see here, you can see I have drawn here the plan of staircase and the elevation of staircase. This plan and elevation I have taken from this AutoCAD file, or I have taken from the drawing of our building, which we have analyzed in this video lecture series. You can also go through our previous lectures to see there. Let's look here. This is the plan and this is the elevation of staircase. Some input data I have written on the left hand side, that is the height between floors is 2.84 meter. So since our height between floors is 2.84 meter, our height between the starting landing slab and the mid landing slab will be half of this height, that is 2.84 divided by 2 is 1.42 meter. Our riser is 0.18 meter or 180 mm. The height of our riser is 180 mm. The width of our tread is 250 mm, so 0.25 meter. Our width of flight and landing width, that is the width of our stairs, is 1.07 meter. You can see here, this is the width of our staircase, and also our landing width, that is the width of our mid landing slab, is also 1.07 meter. And I have written here landing width 2. Landing width 2 means the starting landing slab, that is here. For this landing slab or this slab, our width is 1.78 meter. So we have different width for these two landing slabs. So one is 1.78 meter and another is 1.07 meter. And for loading, imposed load 3 kilonewton per meter square. We discussed about loads on staircase in our previous lecture also. In case of residential buildings, so we can take the imposed load on staircases 3 kilonewton per meter square. I have assumed the floor finish to be 1 kilonewton per meter square. You can calculate your floor finish based on the material that you will be using on the staircase. You may use different types of tiles, marbles or granite, and you can find the density, or you can find the unit weight of those materials and then multiply that unit weight with the thickness of the floor finish that you are going to use, and then calculate the floor finish load in kilonewton per meter square. For this purpose, I have only assumed floor finish to be 1 kilonewton per meter square. And assume that the stair is to be supported on beams of width 0.23 meter. Let's see in our diagram here. Here elevation, this line that I have drawn at the ends, this represents the end of these slabs. And if you draw further, then you can see that our staircase is supported on a beam of width 230 mm. This is the column. Outer lines are the column, and then inside it is supported by beams of width 230 mm. Or this beam may be attached here also. Let me draw this again. Here. Our slab is supported on beams of width 230 mm. So this is our beams supporting the slabs. And we assume our grade of concrete is M20, that is compressive strength is 20 Newton per mm square, and grade of steel is 500 Newton per mm square. So let's begin with calculation of loads. First we have calculated here root under r square plus t square. That means r is the height of the riser and t is the width of the tread. We calculated this because we need this value here to calculate. We will see that in next section in our Excel sheet here. We need this value 0.30 to calculate the self weight of waste slab. We will see how this value is used. We just calculated the value here. Now effective span will be our center to center distance between the supports. So if you don't remember, you can go back to our previous lecture on design of staircase. There we talked about some codal provisions regarding the center to center or regarding the effective span of staircase. And for our staircase, which is a dog-legged staircase supported on two beams on the sides, that means we have a beam underneath this section here and we have a beam underneath this section here. So our landing slab is supported on two beams and our staircase is spanning longitudinally. For this type of staircase, our center to center distance between the supports will be our effective span. So how do we calculate this 4.83? You can add this 1.78 plus 1.75 plus 1.07 plus half the width of beam on one side and another half the width of beam on another side. So it will be 0.23 by 2, half the width. Our width of beam is 230 mm, so 0.23 by 2 plus 1.78 plus 1.75 plus 1.07 plus 0.23 by 2 again. You will get the effective span to be 4.83 meter. Now we begin our design by assuming the thickness of our waste slab is L by 20, where L is the effective span. So 4.83 by 20 or 4,830 millimeters by 20, you get 241.5 millimeters, say 250 mm. We round up this value to the nearest 50 value, so we get this to be 250 mm. Now assume clear cover is 20 mm and the diameter of bars used in our staircase is 12 mm. So we get our effective depth to be 224 mm. That means 250 minus 20 minus 12 divided by 2, you get the effective depth to be 224 mm. Now we have determined or we have assumed a thickness of waste slab for the calculation of loads here. So first we calculate the load on going on projected plan area. That means if you remember what it meant by going, this is the going of our staircase flight. Since our waste slab is inclined here, we have to have a horizontal projection of this flight. So for this whole staircase, if you make a projection, then you get this here. You get this horizontal projection here, and this whole distance is termed as the width of our or the going of our staircase. So we are going to find the loads acting on this projected plan or on this going of our staircase. So unit weight of concrete we suppose or we take it to be 25 kilonewton per meter cube. Self weight of waste slab. So how do we get this value of self weight of waste slab? Since this is the projected plan area, let's look at the diagram here. We know that this is our tread and its thickness or its width is 250 mm, and this is our riser and its width is or its height is 180 mm. Now previously we calculated this value r square plus t square. So what does this value give? This inclined length of this step you get by using this value. In this right angle triangle you get the value of this inclined length using the formula here, root under r square plus t square. That you get nearly to be 300 mm. Calculate yourself also, you can see this inclined length value you get to be 300 mm. This width of the staircase slab or thickness of our staircase slab, thickness of our waste slab, we have assumed to be 240 mm here. Here it is 250 mm, so it won't matter much. Let's see here. Let's say this thickness of our waste slab is 240 mm or even 250 mm, the value won't differ much. Then this straight line height of this slab you get to be 240. That means the thickness of this waste slab into 300. That means the length of this inclined portion divided by 250. 250 means the width of this staircase or the width of this tread. So using this formula you get the vertical height of this slab, and by multiplying this value with the unit weight you get the self weight of waste slab, which comes out to be 7.50 kilonewton per meter square. And self weight of steps, how do we determine the self weight of steps? You can determine this self weight by multiplying this unit weight, which is 25, into the height of our riser, which is 0.18 meter. 0.18 meter divided by 2. So if you use this formula, unit weight into height of riser divided by 2, you get the self weight of steps in kilonewton per meter square. Now floor finish load, we have already taken it to be 1, imposed load 3. Now add these 4 different types of load: self weight of waste slab, self weight of steps, floor finish and imposed load, to get the total load, and multiply this total load by a factor of 1.5 to get the factored load. You get 20.625 kilonewton per meter square to be the factored load on the projected plan area of our staircase. Now we have found the load on projected plan area, but we also have to find the load on our landing. The loading will be the same as in the case of projected plan area, except that there will be no steps on our landing, so you don't have to include the weight of steps. So let's see here again. For the load on landing, remember this value first, 20.625 kilonewton per meter square. Now the load on landing, first the self weight of waste slab will be 6.25 kilonewton per meter square. This value you got by multiplying the unit weight of concrete with the depth of our slab. Since our load or our landing is already horizontal, we don't need this much calculation that we have done previously to determine the vertical thickness of our slab. We can just multiply the unit weight of concrete with the thickness of slab to determine the self weight of that landing slab. Here I have written self weight of waste slab. This is not waste slab. Make correction here. This will be landing slab. So self weight 6.25, floor finish same, imposed load same. Now add these 3 loads to get the total load, which you get to be 10.25 kilonewton per meter square. Hence factored load will be 1.5 into this value, which comes out to be 15.38 kilonewton per meter square. So we got the factored load on our projected plan area 20.625 and factored load on landing will be 15.38. Now after determining the load, we have to determine the bending moment because we need the value of bending moment to calculate the reinforcement in our slab section. So to calculate the bending moment, I have made some calculations here. I did it with my hand and I have posted a screenshot of my calculation. So let's see here, if you call this point A and if you call this point B, AB represents our projected plan of our staircase. Let's see here, first the distance from A to, let's call this now C and D. AC represents the length of our first landing slab, and this length will be the clear length of that landing slab, which was 1.78 meter plus half the thickness of beam on which this landing slab is supported. So 1.78 plus 0.23 by 2, which comes out to be 1.895 meter. This second portion CD represents the projected plan area of our staircase slab, which is 1.75 meter, and this third portion DB represents the mid landing slab, our second slab, whose clear distance or clear width is 1.07 meter plus half the width of beam. The total length comes out to be 1.185 meter. So this represents, AB represents our staircase slab, and the load acting on this slab is, we calculated that the load acting on our landing slab was 15.38 kilonewton per meter square, which is our factored load, while the load acting on our staircase, that is projected plan area of our west slab, was 20.625 kilonewton per meter square. We just derived these values in our previous sections. Now suppose that reactionate A is R1 and reactionate B is RB. These three loads are the uniformly distributed loads acting on our staircase slab. We can use the equations of statics to determine the reaction. First, I have determined reaction R1 here by taking the moment about B. So if you take the moment about B, R2 will not give any moment. The moment will be given by these three loads and R1. So you can use that equation of statics. I won't be going into detail for this because you already know about it. You get the reaction R1 to be 41.06 kilonewton per meter. And if you perform this summation of forces in vertical direction and equate them to 0, you get R2, which comes out to be 42.40 kilonewton per meter. That is, the reaction at R2 is a little bit greater than reaction at R1. Remember that if our slab had equal width in both this initial landing slab and the mid landing slab, if the width of our slab was the same, then these reactions would also come out to be the same. But since our width is different here, 1.895 and 1.185, then the reaction at R2 is greater than reaction at R1. Now we have to find the maximum bending moment in this section or in any section. We don't know where the maximum bending moment lies. If it was symmetrical, if our load distribution was symmetrical, then we could say that the maximum bending moment would lie at the center of this section. But since it is unsymmetrical, first we calculate the bending moment at section X. We have fixed a section X here, and considering the loads on the left hand side of this section, we calculate the bending moment. So R1 into X is the bending moment given by this reaction. This 15.38 kilonewton per meter square gives this bending moment, and the load that is to the left of X, this 20.625 kilonewton per meter square, this portion gives us this bending moment. Now to find this, first this bending moment at X comes out to be an equation. It is a quadratic equation in X because here you get x square here. To calculate the maximum bending moment, we know that the first derivative of this bending moment with respect to X should be 0. So if you perform the derivative of equation 1 and equate it to 0, you get X to be 2.473 meter. So that means our bending moment is maximum at a distance of 2.473 meter from A. This 2.473 meter lies in this central load portion, somewhere in this central load portion. Now use the same value of x that you got here in equation 1 to find the maximum bending moment. You get the maximum bending moment to be 53.64 kilonewton meter per meter. So now after finding the maximum bending moment, now we can find the reinforcement requirement. And to calculate the reinforcement requirement, we take the help of table 2 in SP 16 1980. Table 2 gives us the flexure reinforcement percentage for singly reinforced section here. Let's see here, our maximum bending moment we got to be 53.64 kilonewton meter per meter. Calculate mu by bd square, where width is 1 meter, that is 1000 mm, and d is the effective depth of slab, which we have already calculated above. We get mu by bd square to be 1.06. After calculating this, now let's go to table. The table gives us here the reinforcement percentage for different values of mu by bd square and different values of fy. And remember that table 2 is for concrete grade M20. If you have used a different concrete grade, then you may have to look at a different table. So let's see that mu by bd square, our value is 1.06. If you keep on looking down, you get this 1.05 value. Now you can either interpolate between this 1.05 and 1.10, and you can get a value in between. But for my own easiness, I have just assumed that 1.05 is almost equal to 1.06, and I have just taken the value corresponding to this 1.05 here. So we got our mu by bd square in this first column. Now our grade of steel is 500 Newton per mm square. So I have to look at this first, second, third, fourth, fifth, sixth column. Sixth column corresponding to this 1.05. Our percentage of steel reinforcement value is 0.258. So we take PT to be 0.258. Now you can calculate the area of reinforcement. Since we got percentage to be 0.258, this area of reinforcement you can calculate as 0.258 percentage of BD. BD means B will be 1000 mm and D will be the effective depth of slab, which you get to be 577.92 millimeter square per meter. This is per meter since we are taking the width of slab to be 1 meter at the moment. Now since we are using 12 mm diameter bars, you can calculate the required spacing of 12 mm diameter bars. Because we already have the reinforcement required per meter, and using this reinforcement requirement, you can calculate the spacing by using formula, and you get spacing to be 195.53 millimeter. So we get the required reinforcement to be provided as 12 mm diameter bar set, 195 millimeter center to center. And finally, for distribution steel, we take the area of reinforcement to be 0.12 percentage, because 0.12 percentage is the, if you remember, it is the minimum requirement of reinforcement in slab for high strength bars. So 0.12% you get to be 300 mm square per meter, and if you are using 10 mm diameter bars for distribution steel, the spacing will be 260 mm. So we provide distribution steel as 10 mm diameter bar set, 260 mm center to center. So this completes our design process. And for detailing, you can just go to our previous video and look at detailing, where to keep or how to keep the main bars, how to keep the distribution steel, how to perform the detailing, what to do at the supports for negative moments. All has been discussed in our previous lecture. You can look there and then do the detailing by yourself. So here we got, before ending, let's just see here, we got our main reinforcement bars to be 12 mm diameter set, 195 mm center to center. Remember that this is just our first trial, and you cannot be sure that you will get an optimized section in the first trial itself. If you go up and see here, you can see that we have taken the overall depth of our slab to be 250 mm, and this 250 mm is a very large depth. Aesthetically or architecturally also, this depth is not very much wanted by the clients or wanted by any person building a residential house, because this 250 mm is a very big thickness for the slab. So what you can do is you can just decrease the thickness at a certain interval, and you can just optimize your design by performing all these solutions after this. So for doing that, this type of Excel sheet won't be suitable. You should have an Excel sheet linked with all the formulas. And in such a type of Excel sheet, once you decrease the depth, then all the calculations will be automatically adjusted and you will be provided with the final result. So I prepared this Excel sheet only for explanation for the purpose of this lecture. What you have to do is, once you have performed the calculation for the first time, you may have to decrease or increase the depth and then optimize your design, and that process will be the same as what we have discussed here after this step. So do not forget to optimize your structural sections also. So this is the end of our lecture on design of this dog-legged staircase. I think this is our lecture 15 for our lecture series on RCC resistant design of residential building, and this might be the last lecture of this particular lecture series. Many of our viewers or those of you who have commented under our videos have also asked for the design of other RCC structural sections like shear wall or basement wall. I did not cover those design in this lecture series because this lecture series is only interested with the design of a residential building, and in most of the cases or in many cases our residential buildings do not require a basement wall or shear wall. But be sure that when we start a new lecture series, and in that lecture series when we discussed about the design of tall buildings or commercial buildings, then in that lecture series we will also be discussing with the design of shear walls or basement wall and other structures, other RCC structural sections also. So this will be the end of our lecture. We'll meet again soon. We are also left with continuing our other two lecture series. One is concerned with the detailing and another is concerned with the response spectrum analysis. So we will meet again soon. Thank you.